So recall from last time, in lecture 2, we were really talking about the challenges of recognition and trying to hone in on this idea of a data-driven approach. We talked about this idea of image classification, talked about why it's hard. There's this semantic gap between the giant grid of numbers that the computer sees and the actual image that you see. We talked about various challenges regarding this around illumination, deformation, et cetera, and why this is actually a really, really hard problem, even though it's super easy for people to do with their human eyes and human visual system. Then also recall last time we talked about the k-nearest neighbor classifier as kind of a simple introduction to this whole data-driven mindset. We talked about the CFAR10 dataset, where you can see an example of these images on the upper left here, where CFAR10 gives you these 10 different categories, airplane, automobile, whatnot. And we talked about how the k-nearest neighbor classifier can be used to learn decision boundaries to separate these data points into classes based on the training data. This also led us to a discussion of the idea of cross-validation and setting hyperparameters by dividing your data into train, validation, and test sets. Then also recall last time we talked about linear classification as the first sort of building block as we move toward neural networks. Recall that the linear classifier is an example of a parametric classifier where all of our knowledge about the training data gets summarized into this parameter matrix W that is set during the process of training. And this linear classifier, recall, is super simple, where we're going to take the image and stretch it out into a long vector. So here the image is X, and then we take that image, which might be 32 by 32 by 3 pixels, stretch it out into a long column vector of 32 times 32 times 3 entries, where the 3, again, where the 32 and 32 are the height and width, and the 3 give you the 3 color channels, red, green, blue. Then there exists some parameter matrix, W, which will take this long column vector representing the image pixels and convert this and give you 10 numbers, giving scores for each of the 10 classes in the case of CFAR10, where we kind of had this interpretation where larger values of those scores, so a larger value for the cat class means the classifier thinks that the cat is more likely for that image, and lower values for maybe the dog or car class indicate lower probabilities of those classes being present in the image. Also, so I think this point was a little bit unclear last time, that linear classification has this interpretation as learning templates per class, where if you look at the diagram on the lower left, you think that so for every pixel in the image and for every one of our 10 classes, there exists some entry in this matrix W telling us how much does that pixel influence that class. So that means that each of these rows in the matrix W ends up corresponding to a template for the class. And if we take those rows and unravel, so each of those rows, again, corresponds to a weighting between the pixel values of the image and that class. So if we take that row and unravel it back into an image, then we can visualize the learned template for each of these classes. We also had this interpretation of linear classification as learning linear decision boundaries between pixels in some high-dimensional space, where the dimensions of the space correspond to the values of the pixel intensity values of the image. So this is kind of where we left off last time. And so where we kind of ended up last time is we've got this idea of a linear classifier, and we didn't talk about how to actually choose the W, how to actually use the training data to determine which value of W should be best. So kind of where we stopped off at is that for some setting of W, we can use this W to come up with 10 with our class scores for any image. So, and some of these class scores might be better or worse. So here in this simple example, we've shown maybe just a training data set of 3 images, along with the 10 class scores predicted for some value of W for those images. And you can see that some of these scores are better or worse than others. So for example, in the image on the left, if you look up, it's actually a cat because you're a human and you can tell these things. But if we look at the assigned probabilities, well, not probabilities, but scores, then the classifier, maybe for this setting of W, gave the cat class a score of 2.9 for this image, whereas the frog class gave 3.78. So maybe the classifier is doing not so good on this image. That's bad. We wanted the true class to be actually the highest class score. Whereas for some of these other examples, like the car, for example, you see that the automobile class has a score of 6, which is much higher than any of the others, so that's good. And the frog, the predicted scores are maybe -4, which is much lower than all the other ones, so that's actually bad. So this is kind of a hand-wavy approach, just kind of looking at the scores and eyeballing which ones are good and which ones are bad. But to actually write algorithms about these things and to actually determine automatically which W will be best, we need some way to quantify the badness of any particular W. And that's this function that takes in a W, looks at the scores, and then tells us how bad quantitatively is that W, is something that we'll call a loss function. And in this lecture, we'll see a couple examples of different loss functions that you can use for this image classification problem. So then once we've got this idea of a loss function, this allows us to quantify for any given value of W, how good or bad is it. But then we actually need to come up with an efficient procedure for searching through the space of all possible W's and actually come up with what is the correct value of W that is the least bad. And this process will be an optimization procedure, and we'll talk more about that in this lecture. So I'm going to shrink this example a little bit because 10 classes is a little bit unwieldy. So we'll kind of work with this kind of tiny toy data set of 3 examples and 3 classes going forward in this lecture. Again, in this example, like the cat is maybe not so correctly classified. The car is correctly classified. And the frog it got this setting of W got this frog image totally wrong because the frog score is much lower than the others. So to formalize this a little bit, usually when we talk about a loss function, we imagine that we have some training data set of x's and y's, usually n examples of these, where the x's are the inputs to the algorithm. In the image classification case, the x's would be the actually pixel values of your images. And the y's will be the things you want your algorithm to predict. We usually call these the labels or the targets. So in the case of image classification, remember, we're trying to categorize each image for CFAR 10 into one of 10 categories. So the label y here will be an integer between 1 and 10, or maybe between 0 and 9, depending on what programming language you're using. But it'll be an integer telling you what is the correct category for each one of those images x. And now our loss function will denote li to denote so then we have this prediction function x, which takes in our example x and our weight matrix w and makes some prediction for y. In the case of image classification, these will be our 10 numbers. Then we'll define some loss function li, which will take in the predicted scores coming out of the function f, together with the true target or label y, and give us some quantitative value for how bad those predictions are for that training example. And now the final loss L will be the average of these losses summed over the entire data set, over each of the n examples in our data set. So this is actually a very general formulation and actually extends even beyond image classification. Kind of as we move forward and see other examples of tasks in deep learning, the kind of generic setup is that for any task, you have some x's and y's, and you want to write down some loss function that quantifies exactly how happy you are with your particular parameter settings w, and then you'll eventually search over the space of w to find the w that minimizes the loss on your training data. So as a first example of a concrete loss function that is a nice thing to work with in image classification, we'll talk about the multi-class SVM loss. You may have seen the binary SVM or support vector machine in CS229. And the multi-class SVM is a generalization of that to handle multiple classes. In the binary SVM case, as you may have seen in 229, you only had 2 classes. Each example x was going to be classified as either a positive or negative example. But now we have 10 categories. So we need to generalize this notion to handle multiple classes. So this loss function has kind of a funny functional form. So we'll walk through it in quite a bit of detail over the next couple of slides. But what this is saying is that the loss li for any individual example, the way we'll compute it is we're going to perform a sum over all of the categories y except for the true category yi. So we're going to sum over all the incorrect categories, and then we're going to compare the score of the correct category and the score of the incorrect category. And now, if the score for the correct category is greater than the score of the incorrect category, greater than the incorrect score by some safety margin that we set to 1, if that's the case, that means that the true score is much or the score for the true category is, if it's much larger than any of the false categories, then we'll get a loss of 0. And we'll sum this up over all of the incorrect categories for our image, and this will give us our final loss for this one example in the data set. And again, we'll take the average of this loss over the whole training data set. So this kind of like if-then statement, like if the true class score is much larger than the others, this kind of if-then formulation, we often compactify into this single max of 0 sj minus syij plus 1 thing. But I always find that notation a little bit confusing, and it always helps me to write it out in this sort of case-based notation to figure out exactly what the two cases are and what's going on. And by the way, this style of loss function, where we take max of 0 and some other quantity, is often referred to as some type of a hinge loss. And this name comes from the shape of the graph when you go and plot it. So here, the x-axis corresponds to the SYI. That is the score of the true class for some training example. And now the y-axis is the loss. And you can see that as the score for the true category for this example increases, then the loss will go down linearly until we get to above this safety margin, and after which the loss will be 0 because we've already correctly classified this example. Yeah, so the question is, in terms of notation, what is S and what is SYI in particular? So the S's are the predicted scores for the classes that are coming out of the classifier. So like if 1 is the cat class and 2 is the dog class, then S1 and S2 would be the cat and dog scores respectively. And remember we said that YI was the category of the ground truth label for the example, which is some integer. So then S sub Y sub I, sorry for the double subscript, that corresponds to the score of the true class for the ith example in the training set. Yeah, the question is, what exactly is this computing here? It's a little bit funny. I think it'll become more clear when we walk through an explicit example. But in some sense, what this loss is saying is that we are happy if the true score is much higher than all the other scores. It needs to be higher than all the other scores by some safety margin. And if the true score is not high enough, greater than any of the other scores, then we will incur some loss, and that will be bad. So this might make a little bit more sense if you walk through an explicit example for this tiny 3-example data set. So here, remember, I've sort of removed the case-based notation and just switching back to the 0, 1 notation. And now if we think about computing this multi-class SVM loss for just this first training example on the left, then remember, we're going to loop over all of the incorrect classes. So for this example, cat is the correct class. So we're going to loop over the car and frog classes. And now for car, we're going to look at the car score, 5.1, minus the cat score, 3.2, plus 1. When we're comparing cat and car, we expect to incur some loss here because the car score is greater than the cat score, which is bad. So for this one class, for this one example, we'll incur a loss of 2.9. And then when we go and compare the cat score and the frog score, we see that cat is 3.2, frog is minus 1.7. So cat is more than 1 greater than frog, which means that between these two classes, we incur 0 loss. So then the multi-class SVM loss for this training example will be the sum of the losses across each of these pairs of classes, which will be 2.9 plus 0, which is 2.9. Which is sort of saying that 2.9 is a quantitative measure of how much our classifier screwed up on this one training example. And then if we repeat this procedure for this next car image, then again the true class is car, so we're going to iterate over all of the other categories. When we compare the car and the cat score, we see that car is more than 1 greater than cat, so we get no loss here. When we compare car and frog, we again see that the car score is more than 1 greater than frog, so we get, again, no loss here. And our total loss for this training example is 0. And now, I think you hopefully get the picture by now, but if you go look at frog, now frog, we again compare frog and cat, incur quite a lot of loss because the frog score is very low. Compare frog and car, incur a lot of loss because the score is very low. And then our loss for this example is 12.9. And then our final loss for the entire data set is the average of these losses across the different examples. So when you sum those out, it comes to about 5.3. So then it's sort of, this is our quantitative measure that our classifier is 5.3 bad on this data set. Yeah, the question is, how do you choose the +1? That's actually a really great question. It seems like kind of an arbitrary choice here. Like, it's the only constant that appears in the loss function, and that seems to offend your aesthetic sensibilities a bit, maybe. But it turns out that this is somewhat of an arbitrary choice. You can kind of set the, because we don't actually care about the absolute values of the scores in this loss function. We only care about the relative differences between the scores. We only care that the correct score is much greater than the incorrect scores. So in fact, if you imagine scaling up your whole W up or down, then it kind of rescales all the scores correspondingly. And if you kind of work through the details, and there's a detailed derivation of this in the course notes online, you find that this choice of 1 actually doesn't matter. That this free parameter of 1 kind of washes out and is canceled with the scale, like the overall setting of the scale in W. So then I think it's kind of useful to think about a couple different questions to try to understand intuitively what this loss is doing. So the first question is, what's going to happen to the loss if we change the scores of the car image just a little bit? Yeah, so the answer is that if we jiggle the scores for this car image a little bit, the loss will not change. So the SVM loss, remember, the only thing it cares about is getting the correct score to be greater than 1 more than the incorrect scores. But in this case, the car score is already quite a bit larger than the others. So if the scores for this class change, for this example, change just a little bit, this margin of 1 will still be retained, and the loss will not change. We'll still get 0 loss. The next question, what's the min and max possible loss for SVM? So the minimum loss is 0, because if you can imagine that across all the classes, if our correct score was much larger, then we'll incur 0 loss across all the classes, and it'll be 0. And if you think back to this hinge loss plot that we had, then you can see that if the correct score goes very, very negative, then we could incur potentially infinite loss. So the min is 0 and the max is infinity. Another question, sort of when you initialize these things and start training from scratch, usually you kind of initialize W with some small random values. As a result, your scores tend to be sort of small, uniform random values at the beginning of training. And then the question is that if all of your S's, if all of the scores are approximately 0 and approximately equal, then what kind of loss do you expect when you're using the multi-class SVM? Yeah, so the answer is number of classes minus 1, because remember that if we're looping over all of the incorrect classes, so we're looping over C minus 1 classes, within each of those classes, the two S's will be about the same, so we'll get a loss of 1 because of the margin, and we'll get C minus 1. So this is actually kind of useful, because this is a useful debugging strategy when you're using these things, that when you start off training, you should think about what you expect your loss to be. And if the loss you actually see at the start of training at that first iteration is not equal to C minus 1 in this case, that means you probably have a bug and you should go check your code. So this is actually kind of a useful thing to be checking in practice. Another question, what happens if, so I said we're summing an SVM over the incorrect classes. What happens if this sum is also over the correct class, if we just go over everything? Yeah, so the answer is that the loss increases by 1. And I think the reason that we do this in practice is because normally loss of 0 is kind of has this nice interpretation that you're not losing at all, so that's nice. So I think your answers wouldn't really change. You would end up finding the same classifier if you actually looped over all the categories, but it's just by conventions we omit the correct class so that our minimum loss is 0. So another question, what if we used mean instead of sum here? Yeah, the answer is that it doesn't change. So the number of classes is going to be fixed ahead of time when we select our data set. So that's just rescaling the whole loss function by a constant. So it doesn't really matter. It'll sort of wash out with all the other scale things because we don't actually care about the true values of the scores. Or the true value of the loss, for that matter. So now here's another example. What if we change this loss formulation and we actually added a square term on top of this max? Would this end up being the same problem, or would this be a different classification algorithm? Yes, this would be different. So here the idea is that we're kind of changing the trade-offs between good and badness in kind of a nonlinear way. So this would end up actually computing a different loss function. This idea of a squared hinge loss actually does get used sometimes in practice. So that's kind of another trick to have in your bag when you're making up your own loss functions for your own problems. Yeah, so the question is, why would you ever consider using a squared loss instead of a non-squared loss? And the whole point of a loss function is to kind of quantify how bad are different mistakes. And if the classifier is making different sorts of mistakes, how do we weigh off the different trade-offs between different types of mistakes the classifier might make? So if you're using a squared loss, that sort of says that things that are very, very bad are now going to be squared bad. So that's like really, really bad. Like we don't want anything that's totally catastrophically misclassified. Whereas if you're using this hinge loss, then we don't actually care between being a little bit wrong and being a lot wrong. Kind of like if an example is a lot wrong and we increase it and make it a little bit less wrong, that's kind of the same goodness as an example which was only a little bit wrong and then increasing it to be a little bit more right. So that's a little bit hand-wavy, but this idea of using a linear versus a square is a way to quantify how much we care about different categories of errors. And this is definitely something that you should think about when you're actually applying these things in practice. Because the loss function is the way that you tell your algorithm what types of errors you care about and what types of errors it should trade off against. So that's actually super important in practice depending on your application.
이번 시간에는 로스 펑션, 손실함수와 옵티마이제이션, 최적화에 대해서 강의하도록 하겠습니다. 지난 시간에는 레코그니션의 도전 과제들에 대해서 이야기했습니다. 먼저 카메라가 움직임에 따라서 뷰 포인트가 바뀐다는 문제가 있었고 일루미네이션, 디포메이션, 오클루전, 백그라운드와 클러터되는 문제, 인트라클래스 베리에이션 문제들이 있었습니다. 이미지 클래시피케이션은 기존의 AI 알고리즘으로는 잘 동작하지 않고 데이터 드리븐 어프로치를 써야 합니다. 그 예로서 KNN 알고리즘을 사용해서 C510 데이터셋에서 에어플레인부터 트럭까지 10개의 클래스들을 분류하는 사례를 소개하였습니다. 이때 데이터를 트레이닝 데이터와 테스트 데이터로 나눌 수 있는데 더 좋은 방법은 트레인 데이터, 밸리데이션 데이터, 테스트 데이터로 나눠서 밸리데이션 데이터를 통해서 하이퍼 파라미터 값을 찾는 것이 더 좋은 방법이라고 설명했습니다. 리니어 클래시파이어는 뉴럴 네트워크 시스템을 구현하는데 핵심적인 기본 개념이라는 것을 설명했습니다. 여기서 함수 f는 input 이미지 x와 weight matrix w와 bias vector b로 구성이 되어 있습니다. 트레이닝을 통해서 w와 b 값이 아웃풋 에러를 줄이도록 조정해 나가는 것이 학습이라는 것을 설명했습니다. 다음은 리니어 클래시파이어가 3개의 인풋 이미지에 대해서 10개의 클래스에 대한 스코어 값을 제시한 것입니다. 이때 오토모빌의 경우에는 6.04의 가장 높은 스코어로 올바른 예측이 나왔지만 캣과 프로그 경우에는 그렇지 못했습니다. 여기서 우리가 다음 단계로 해야 되는 일, to do는 스코어로부터 로스 펑션을 정의하는 것입니다. 그 다음에는 로스 펑션을 미니마이즈하게 해서 w와 b 같은 파라메타들을 어떻게 하면 효율적으로 변화할지에 대한 방법을 찾는 것입니다. 이를 옵티마이제이션, 최적화라고 합니다. 다음은 3개의 트레이닝 이그젬플과 3개의 클래스를 가정한 것입니다. 어떤 w에 대해서 f=wx라는 리니어 클래시파이어를 사용하면 다음과 같은 결과를 얻을 수 있습니다. 이때 칼의 경우에는 4.9의 가장 높은 스코어를 얻어서 바람직한 결과를 얻었지만 캣과 프로그의 경우에는 각각 두 번째와 세 번째의 높은 점수를 얻어서 w와 b를 조절해야 될 필요성이 제시되었습니다. 로스 함수는 현재 클래시파이어가 얼마나 잘 동작하는지를 이야기해 줍니다. 데이터셋 이그샘플이 주어진 것을 xi, yi, i는 1부터 n까지의 집합으로 표시할 수 있습니다. 여기서 xi는 이미지고 yi는 인티저 레이블입니다. 데이터셋에 대한 로스는 각 이그샘플에 대한 로스의 합으로 다음과 같이 표시될 수 있습니다. L은 1 나누기 n, 시그마 i는 1부터 n까지 li 각각의 로스입니다. 멀티클래스 SVM 로스는 example xi, yi에 대해서 스코어 벡터 s를 fxiw로 하고 다음과 같이 정의할 수 있습니다. 여기서 i가 example의 인덱스이고 j가 클래스의 인덱스라고 할 때 yi는 example의 레이블, syi는 example의 스코어, sj는 클래스의 스코어가 됩니다. 따라서 SVM의 로스 펑션 li는 summation max 0, sj-syi 플러스 1이 됩니다. 멀티클래스 SVM 로스를 그래프로 나타내면 파란색 선처럼 표시할 수 있습니다. 이를 힌지 로스라고도 합니다. 고양이 이미지 사례에서 로스 값을 계산하면 2.9가 나옵니다. 자동차 경우에는 정확한 값을 예측하였기 때문에 로스 값이 0이 나옵니다. 개구리의 경우에는 로스 값이 12.9라는 가장 큰 값이 나왔습니다. 로스 값 L1, L2, L3가 각각 2.9, 0, 12.9가 나왔기 때문에 전체 로스 값은 5.27이 나왔습니다. 로스 값을 계산하는데 다른 함수를 사용할 수도 있습니다. 만일 우리가 주어진 식처럼 맥스 값에 자승을 취하면 스코어의 차이가 클수록 로스 값은 더 빠르게 상승할 것입니다.